In this series of video lectures on quantum theory, today I shall present action small, action large, Wilson-Sommerfeld quantisation rule and its applications to different periodic systems. Let me start. First, a dynamic particle may have various variables like position, linear momentum, azimuthal angle, angular momentum, energy, time, etc. Whenever the product of two variables is having the dimension of Planck's constant h, that is m l square t to the power minus 1, these two variables we call conjugate variables, or better canonically conjugate variables. Such variables are position and linear momentum, px, azimuthal angle, theta, and angular momentum, p phi, time or energy and time. Product of these two conjugate variables, position and momentum, azimuthal and angular momentum, energy and time, this product we call the action or the characteristic action of these dynamic particles. When the action, and this action is denoted by Jc, characteristic action. When Jc is much greater than h, which generally occurs for these macroscopic bodies, it is called action large. And the Newtonian mechanics is sufficient to describe or interpret the motions of these macroscopic bodies, which characteristic action is very high. But when Jc almost equal to h or comparable to the value of this Planck's constant, it is called the action small. And for this action small, subatomic particles are generally having the action small, and quantum mechanics has to be applied to interpret the motions of these subatomic particles. When this when the particle executing the periodic motion such that the one of the conjugate variables will change periodically, means having the values, same repeating values after certain time intervals or position intervals, or both will be having the periodic motions. And for that for the systems having the periodic motions, the action integral integrated over one period of motion is called action integral, or we can call phase integral or one phase motions, phase integral. And this phase integral is denoted by the integration integrated over the whole one period of motions and JC. JC. This is called cyclic integral. For example, we can say this integration over a period of motions. It is Px and dx, or integration over one period of motion. It is P phi and d phi, or integration over in one period of motion E and dt, etc. For the systems executing the periodic motions, in 1915, W. Wilson and A. Sommerfeld stated one rule, generalized rule. Independently, they produced this generalized rule, and this rule is very much useful to determine or to calculate the discrete values of some properties for the systems executing the periodic motions. Wilson and Sommerfeld both are very famous scientists. You know, Wilson is very famous for its cloud chamber experiment, and he had been awarded Nobel Prize. Sommerfeld is also important. He is also very famous scientist whose elliptical motion of the hydrogen atom is very popular and was very popular at that time. They stated in 1915, W. Wilson and A. Sommerfeld stated that for system executing periodic motion, the phase integral of the conjugate pair of variables in each degree of freedom will be integral multiple of Planck's constant h. Mathematically, we can write the integration for one period of motion pk dqk equal to nkh. Pk and qk, these two are the conjugate variables in the same degree of freedom, in kth degree of freedom, and nk is the quantum number in the same degree of freedom, and nk is having the value 0, 1, 2, 3, etc. That is any positive integer including 0. One example I can show the application of this Wilson-Sommerfeld quadrature rule, that now you consider elliptical path of this Sommerfeld, elliptical path of this electron of hydrogen in hydrogen atom. Elliptical path of this electron in hydrogen atom, keeping its nucleus in any of the foci. Suppose here is the nucleus present. Here is the electron. So, whenever this electron is moving in a elliptical path, then its radial distance means the distance of this electron from this nucleus, this r, is changing periodically. After a certain time interval, it comes to its initial position. Not only that, the phi, the azimuthal angle, is also periodically changing with a range of 0 to again it comes after 2 pi. So if we apply this Wilson-Sommerfeld quantization rule to this system, then it is cyclic integral, and PR dr equal to nrh. And another variable, cyclic integral, p phi d phi equal to n phi h. This nr we may call the radial quantum number. a radial quantum number, and this radial quantum number, and n phi, similarly n phi is maybe called the azimuthal quantum number. Both the value having the values, quantum number having the values, the positive integer including the 0. But in the both the cases, 0 is not possible for some other reasons. Its value 1, 2, 3, 4, etc. Now I may cite some examples, some systems executing the periodic motions in which some of the important properties of that system is quantized, having the discrete values. These are the Bohr hydrogen atom, circular motion of the electrons, keeping the nucleus at its center, the free axis rigid rotator, the particle in one-dimensional box, and one-dimensional simple harmonic oscillation. I shall discuss the applications of this Wilson-Sommerfeld quantization rule one after another. In this day, I first take the attempt to get this quantized value of the angular momentum, quantized value of this as the energy, velocity, radius, etc. for Bohr hydrogen atom. For Bohr hydrogen atom, this is one part, or you can say this is part 1 of my lecture, part 1, Bohr hydrogen atom. Bohr hydrogen atom, this is nucleus, and the surrounding this nucleus in a circular path, this electron is revolving. Here the r the radial distance, radial distance remains fixed all the times, but it is the azimuthal angle. This azimuthal angle is changing. Azimuthal is changing periodically with this range 0 to when here it is 0, and when coming after one period of motion it is twice 2 pi. So for this case we can write this quantization rule as phase integral and p phi and d phi equal to nh. N is having the values positive integer. Here phi is changing its position, having the periodic motions, and p phi here remains fixed. As p phi equal to mvr, m is fixed for this electron as we are considering the non-relativistic approach. R is also fixed, this radius, and V is also fixed for this circular motions, as we know the centrifugal force mv square by R is equal to the centripetal force. Centripetal force is Z E square by R square. As these two forces are equal, so that electron is having a stationary orbit or stable orbit, fixed orbit. So V, whenever no force is acting, this velocity will take this steady value mvr. Both all are fixed, so p phi also fixed. We can take this p phi out of this integral sign, and the limit is 0 to 2 pi, and d phi equal to nh. And whenever this integration is done and putting the limit, we have p phi equal to nh by twice pi. Thus we can see the angular momentum of this electron in this circular path is having the quantized value. It has the value n equal to 1, 2, 3, 4, etc. And when p5 may have the value h by 2 pi or 2h by 2 pi or 3h by 2 pi, not the value in between the two or in between the two. This is a very important postulate of this board, and by the use of this postulate and these two conditions, it is possible to calculate this energy value of this hydrogen atom. As we know, this mvr equal to nh by 2 pi. This is one equation. Suppose A. And so V square equal to n square h square divided by 4 pi square into m square r square. Another relation is these two forces are equal. So mv square by r equal to z square by r square. Z is the charge of this positive charge of this nucleus, and it is valid not only for the hydrogen atom but for any one electron system like helium plus, lithium plus 2, etc. So this v square, here also v square equal to z square divided by mr. This one is A and this one suppose B. Equating these two A and B, we get the value of R, and Z square by mr equal to n square h square divided by 4 pi square m square r square. So r equal to n square h square divided by 4 pi square m z square. Now that means r is also quantized, having this certain value n equal to 1, 2, 3, 4, and this one is constant. This one is constant for this hydrogen-like atoms. Now we have this total energy equal to kinetic energy plus a potential energy. And now we are approaching to calculate this energy of this hydrogen atom. Kinetic energy plus potential energy. Kinetic energy equal to half mv square. Putting this value here, we get this one equal to half into z square by r. And the potential energy is equal to minus integral and r into force, into the attractive force of this electron by the nucleus, and this one equal to, by putting this value of this attractive force F, we get minus infinity to r into minus z square by r square into dr, and this will give you the value of z minus z square by r. So this is the potential energy, this is the kinetic energy. It is seen that potential energy is negative and kinetic energy is always positive, but potential energy is double the kinetic energy. Means this attractive potential is much greater than the kinetic energy, and this will prevent this electron to move outside of this periphery of this hydrogen atom, this attractive potential. Now I easily can give you a formula for this E equal to, say, kinetic energy equal to half Z E square by R, and potential energy is minus Z E square by R, and this is equal to minus half Z E square by R. Whenever I shall put this value of R in this equation, I shall get this En, energy of this nth state of this hydrogen atom, equal to 1 by N into minus 2 pi square N Z square e to the power 4 divided by H square, and this energy value is having the negative value N square. This is the negative value, means this electron is bound within this hydrogen atom, and energy required to remove this electron from this periphery of the hydrogen atom, this amount of energy is to be required. And now for hydrogen atom, for a hydrogen atom, atom Z equal to 1, and this M, it is the mass of this electron. It is the mass of this electron, but better it should be replaced by mu reduced mass, M to be replaced by this reduced mass of this hydrogen atom, and reduced mass equal to mass of this nucleus into mass of this electron divided by mass of this nucleus plus mass of this electron. Since the mass of the nucleus is much greater, at least 1836 times greater than mass of this electron, it is almost equal to mass of this electron. Means mass of this electron means reduced mass is equal to mass of this electron. Reduced mass actually describes the contributions of the contribution towards this motion, towards this rotation of this electron nucleus. Here it shows that the electron is rotating and nucleus remains static in its central position. So whenever we shall consider the energy En for this hydrogen atom, this is equal to minus twice pi square and mu e to the power 4 divided by H square. So by this way we can calculate the energy value of this hydrogen atom in any orbit. N may be 1, N may be 2, and energy value we will take this discrete values. In my next lectures, part 2, I shall describe the applications for this free axis rigid rotator and the particle in one-dimensional box and simple harmonic oscillator. Thanks for watching this video which is based on Wilson's Sommerfeld quantisation rule.